Scientists are watching closely after movement was detected along two massive fault lines, and the reason is not simple panic. These deep fractures can stay quiet for years, even centuries, while stress builds silently beneath the surface, now with new signs of motion. Researchers are asking a careful question: was this only a small adjustment, or the beginning of something larger still unfolding underground? In this video, the evidence, the science, and the hidden forces beneath the crust come into focus. If this kind of deep earth story fascinates you, like the video, subscribe to the channel, and stay with us. Across the surface of the planet, the ground appears still at first glance, extending in broad plains, rising into mountains, and falling away into valleys that hold rivers and scattered vegetation. The light of the sun moves slowly across this surface, tracing long shadows over ridges and shallow depressions. From a distance, the land seems fixed, as though it has held this shape for a very long time. Yet the surface is not a single unbroken shell. It is divided into large pieces of rock, each one resting upon deeper layers that move with quiet persistence. The outermost layer of Earth, known as the crust, forms a thin boundary between the atmosphere above and the deeper interior below. This crust is not smooth or continuous. It is segmented, broken into sections that fit together like uneven pieces of a vast and shifting pattern. These sections, often called plates, extend across continents and beneath oceans. Their edges are not always visible, but in many places the boundaries can be traced through the shape of the land itself. Mountain ranges rise where parts of the crust have been pushed together over long spans of time. Valleys open where sections have pulled apart or shifted sideways. Long, narrow lines can sometimes be seen cutting across the terrain, marking places where the ground has fractured. These lines do not always appear as sharp breaks. In some regions, they are subtle, expressed as slight changes in elevation, altered river paths, or aligned ridges that follow a consistent direction for many kilometers. The surface also carries the marks of past movement. Layers of rock that were once horizontal are now tilted or folded. River channels bend in unusual ways, as if redirected by forces that moved the ground beneath them. In dry regions, straight lines stretch across the landscape, revealing the trace of ancient fractures that have shifted again and again. In wetter environments, vegetation may grow differently along these lines, reflecting subtle differences in soil and water flow. The atmosphere above remains calm during long periods, with winds moving slowly across the land and clouds forming and dissolving without disturbance. There is no immediate sign, from this broad perspective, that the ground itself is under tension. The stillness of the air contrasts with the hidden motion beneath the surface. Observations indicate that even when no visible change occurs, the crust continues to adjust, responding to forces that act over distances far larger than any single landscape. Along certain regions, two long fault lines extend across the surface, each one tracing a path that can be followed for hundreds of kilometers. These lines are not isolated features. They are part of a larger network of fractures that divide the crust into shifting sections. Their paths may cross deserts, forests, and populated areas, linking distant environments through a shared structure beneath the ground. In some areas, the fault lines are marked by slight ridges or shallow troughs. In others, they are nearly invisible, hidden beneath soil, vegetation, or human development. Yet their presence can be inferred from the arrangement of natural features. Streams may run along them for a distance before turning away. Hills may align in patterns that follow their direction. The land itself provides quiet evidence of these boundaries. The broader setting includes not only land but also bodies of water that rest upon the same moving crust. Coastlines shift slowly over time, and the seabed carries its own network of fractures. Though the focus remains on the visible surface, it becomes clear that the processes shaping these features extend beyond what can be directly observed. The surface is only the outer expression of deeper motion. The climate interacts with the land in ways that can both conceal and reveal these structures. Rainfall erodes exposed rock, softening sharp edges and filling cracks with sediment. Wind carries dust that settles into low areas, smoothing the surface over time. Vegetation grows in patterns influenced by water availability, sometimes highlighting underlying fractures where moisture collects more easily. These processes act continuously, altering the appearance of the land while the underlying structure persists. From a high vantage point, such as a satellite orbiting above Earth, the arrangement of these features becomes more apparent. Long lines extend across regions, intersecting with others to form a complex network. The scale of these structures becomes clear only when viewed in this way. What appears as a small irregularity on the ground is part of a much larger pattern that spans entire regions. Scientists observe that the positions of these fault lines are not random. They follow the edges of the moving plates that make up the crust. Where two plates meet, the stress generated by their motion is often concentrated. This stress can be released gradually or suddenly, depending on the conditions along the boundary. The surface, though seemingly calm, is shaped by these ongoing interactions. The two fault lines of interest lie within this broader context. Their recent movement has drawn attention because it reflects changes occurring within the larger system. Observations indicate that shifts along these lines are part of a continuing process rather than isolated events. The surface provides the first indication that something has changed, even if the details of that change are not immediately visible. In this outermost view, the focus remains on the landscape as a whole. The ground stretches outward in all directions, carrying within it the record of past motion and the potential for future change. The fault lines are present but not yet examined in detail. They are part of the surface, embedded within the broader environment that defines their setting. The stillness of the visible world continues, with no sudden movement or disturbance. Yet beneath this calm appearance, forces are at work, slowly shaping the land over time. The surface serves as both a record and a boundary, marking the interface between what can be seen and what remains hidden below. A fault line is a fracture in Earth's crust where blocks of rock on either side move in relation to one another. At the scale of a hand sample, a fracture may appear as a simple break through a stone. At the scale of a region, a fault becomes something far larger, stretching across hills, plains, river basins, and mountain fronts. It may continue for hundreds of kilometers, not as a perfectly straight mark but as a connected zone of broken ground, branching strands, crushed rock, and repeated offsets that together show where the crust has been slipping over long periods of time. On the land, a major fault line rarely appears as a single narrow crack. More often it forms a belt of deformation, a broad corridor where motion has affected the surface in many ways. Within this corridor, ridges may be cut and shifted. Valleys may align in a strikingly linear pattern. Small depressions may form where the ground has pulled apart locally. Low scarps, which are step-like breaks in the surface, may run for long distances and mark places where one side has moved in relation to the other. Even when erosion softens these forms, their overall pattern often remains visible. Some faults accommodate sideways motion. In these, one side slides past the other horizontally. Others show vertical movement, lifting one side or dropping the other, Many major faults combine these motions, so the land shifts sideways while also rising or sinking. The exact style depends on the forces acting across the region. Scientists define these motions carefully, but on the surface the result is simple to observe. Features that were once continuous become displaced. A stream channel no longer meets its former path directly. A ridge is cut and offset. Layers of gravel or volcanic ash are no longer in their original alignment. When scientists trace two monster fault lines across a region, they begin with the land itself. They examine topographic maps, aerial images, and satellite views. They walk the ground where exposure is good. They look for repeated patterns that cannot be explained by ordinary erosion alone. If a valley follows a remarkably straight path for a great distance, that may indicate structural control. If several streams are all bent in the same direction where they cross a line, that suggests horizontal movement. If a line of springs appears along a consistent trend, that may point to fractured rock allowing water to rise. Over time, fault lines gather a visible geography of their own. A major strike-slip fault, meaning a fault dominated by sideways motion, may create long troughs and shutter ridges. A shutter ridge forms where a moving block of land shifts across the mouth of a small valley or stream, partly blocking it and forcing water to divert. In extensional settings, where the crust is pulled apart, faults may bound basins that gradually fill with sediment. In compressional settings, where the crust is pushed together, faults may help raise mountain fronts and fold nearby rock layers. Each landscape tells part of the story of the movement, but only within the limits of surface evidence. The two fault lines watched closely by scientists stand out because they are both long-lived structures. They do not represent new breaks in previously untouched rock. They are recurring zones of weakness and motion, active over many cycles of stress accumulation and release. The ground along them has been shaped repeatedly, so the present landform is the product of many episodes rather than one single event. Observations indicate that when such faults move again, they often reactivate older traces already written into the crust. A long fault line is rarely uniform from one end to the other. One segment may cut sharply across exposed bedrock. Another may disappear beneath a blanket of young sediment laid down by rivers or lakes. In urban areas, buildings, roads, and altered drainage can obscure the natural trace. In forested terrain, vegetation may conceal scarps and depressions. Scientists therefore map a fault by combining direct and indirect signs. They do not rely on one isolated crack or one small surface break. Instead, they look for continuity across the region, following the geometry of the line through many changing environments. The width of the fault zone matters as much as its length. Within the main corridor, rock may be intensely fractured, ground into smaller fragments by repeated motion. This crushed material is sometimes called fault gouge when it becomes very fine, or fault breccia when it consists of angular broken pieces. Near the surface, these materials can influence drainage, slope stability, and even vegetation patterns. The line on a map therefore represents a wider damaged zone in the crust, not merely a thin cut. The motion of two nearby or related fault lines can also be understood only in relation to their geometry. Some faults run roughly parallel, sharing regional stress while accommodating movement in different ways. Others intersect or transfer motion through bends and stepovers. A stepover is a place where one fault strand ends or shifts sideways and motion continues onto another strand. These areas are especially important because stress can become concentrated there. On the surface, stepovers may create basins, uplifted blocks, or unusually complex fracture patterns. When recent movement is reported along two monster fault lines, Scientists first ask how the motion fits the existing map of structures. They compare the new displacement with older offsets preserved in terraces, stream channels, or rock units. They assess whether the motion occurred along the main mapped trace or on nearby subsidiary fractures. A subsidiary fault is a smaller branch connected to the main structure. These branches can also move during large events, widening the area affected at the surface. Not every mapped fault line is equally active in the present day. Some preserve ancient motion but show little modern strain. Others continue to accumulate stress and occasionally produce destructive earthquakes. Distinguishing between these states requires careful work. The shape of the landscape helps, but it must be paired with dating of young deposits, measurements of present-day movement, and records of past shaking preserved in sediments and broken layers. Even so, uncertainty remains in some cases. A fault may appear quiet for a long interval and still be capable of sudden movement. At the land surface, the trace of a fault often appears both ordinary and strange. It may run through familiar terrain where farms, roads, and villages sit upon ground shaped by repeated displacement. Nothing in daily appearance demands constant attention, yet the alignment of hills, the offset gullies, the linear valleys, and the abrupt changes in drainage quietly mark a boundary between moving crustal blocks. The fault is not a single wound opening visibly across the whole region. It is a persistent structural line, partly hidden, partly exposed, and written into the topography. In this section, the land is read as a map of fractures. The two fault lines are understood not as isolated cracks but as extensive surface structures with shape, width, history, and measurable displacement. Their traces organize the landscape around them. The broad outer setting now gives way to the lines themselves, still observed from the surface, still held within the visible world of rock, soil, water, and relief. From far above the planet, the ground no longer appears as a familiar landscape of roads, trees, and exposed rock. It becomes a measured surface, divided into pixels, coordinates, and repeating images captured over time. The broad outlines of mountains and basins remain visible, but the scientific focus shifts from shape alone to change. A fault line that seems still to an observer standing nearby can reveal motion when viewed through repeated measurements made from orbit, from aircraft, and from fixed instruments anchored to the land. This distant view does not replace field observation, it extends it, allowing scientists to watch large regions continuously and compare one moment with another. Satellites provide one of the most important ways to detect crustal motion over wide areas. Some circle Earth while sending radar pulses toward the ground. These pulses reflect back to the satellite, carrying information about the distance between the instrument and the surface below. When the same place is observed repeatedly, the returning signals can be compared. Very small changes in position can then be detected. This method, called radar interferometry, compares the phase of returning radar waves from different times. The term phase refers to the position of a wave within its repeating cycle. By measuring changes in that cycle, scientists can infer whether the ground has moved slightly toward or away from the satellite. The power of this method lies in its scale. A single set of satellite observations can cover a broad region that includes mountain fronts, valleys, towns, and remote uninhabited ground. Instead of relying only on a few isolated instruments, scientists can build a regional picture of deformation. Patterns emerge across the surface. Some areas appear stable, others show gradual change, where movement has occurred along a fault. The signal may appear as a sharp boundary between one side and the other, or as a more distributed zone of strain spread across several kilometers. Another important tool is the Global Positioning System, often shortened to GPS. Proper noun acronyms remain standard in science, and here GPS refers to a method of determining position from signals sent by satellites. Ground stations fixed securely into bedrock record their locations again and again. Over time, those locations can be measured with remarkable precision. If one station drifts slowly northward, while another nearby moves less or shifts in a different direction, the relative motion between them reveals how strain is accumulating in the crust. When many such stations operate across a region, the motion of entire crustal blocks can be estimated. These measurements are especially valuable because crustal movement is often slow. A fault may accommodate only a few millimeters or centimeters of motion in a year, depending on the tectonic setting. Such change is too small to notice directly in everyday life, yet over decades it becomes significant. Instruments do not grow impatient with slow processes. They repeat the same observation again and again, building a record that shows whether ground is creeping steadily, remaining locked, or shifting abruptly after an earthquake. Observations indicate that the most important signals often come not from a single dramatic moment, but from long sequences of consistent measurement. Scientists also use high-resolution topographic mapping to compare the shape of the land over time. Airborne laser scanning, often called LiDAR, sends pulses of light toward the ground and measures how long they take to return. From this, a very detailed surface model can be constructed. Vegetation can often be filtered out computationally, revealing the bare earth topography beneath. This is especially useful in regions where fault scarps, offset channels, or subtle linear depressions are hidden by dense plant cover. By comparing LiDAR surveys from different times, researchers may identify fresh deformation or confirm the geometry of older traces. Repeated optical images from satellites and aircraft also contribute to the picture. These images may not measure ground displacement as directly as radar or GPS, but they can show fresh ruptures, landslides, altered drainage, or shifts in surface features after a fault movement. In dry terrain, even a modest new crack or offset can stand out against a relatively bare surface. In wetter or more vegetated regions, the signal may be less obvious, and interpretation becomes harder. For this reason, no single remote method is treated as sufficient on its own. Scientists compare independent measurements and look for agreement across them. When two monster fault lines move within a related time period, the distant view becomes especially important. It allows scientists to ask whether deformation is confined to the main traces or distributed across the surrounding crust. Sometimes movement on one fault is accompanied by subtle changes on neighboring structures. Sometimes broad regional adjustment occurs without a single sharply defined rupture cutting the surface. Remote observations can reveal gradients of motion, patterns of uplift or subsidence, and differences between one segment and another that would be difficult to detect by walking the ground alone. The language of measured change remains cautious. A pattern in radar data may suggest ground displacement, but scientists test it against weather effects, vegetation changes, orbital uncertainties, and signal noise. GPS stations can shift for reasons unrelated to tectonics if their foundations are unstable or if equipment problems arise. Optical images may show apparent change caused by seasonal variation in light, moisture, or land use. For this reason, the distant perspective is not simply accepted at face value. It is examined critically, corrected where possible, and compared with other data sets before conclusions are drawn. Even so, the broad viewers transform the study of active faults. It makes it possible to monitor inaccessible terrain, to revisit the same region frequently, and to measure patterns that span large distances. A fault system that once had to be understood mainly through scattered field sites can now be observed almost as a whole. The result is not a perfect image of crustal motion, but a far clearer one than earlier generations could obtain. Subtle strain that once remained hidden now leaves a measurable signal across the surface. In many cases, the first indication that something important has changed comes from these regional data. Scientists may notice an unusual pattern of displacement in newly processed radar scenes. They may find that GPS stations on opposite sides of a fault have changed relative position in a way that differs from the long-term trend. They may compare new topographic data with earlier surveys and detect fresh rupture or warping. Only after that initial signal emerges do teams often move in closer, combining remote evidence with field investigation and seismic analysis. At this outer observational layer, the fault is still being watched from afar. The emphasis remains on measured motion across a wide region, rather than on the immediate details of the recent shift itself. Earth's surface becomes a mapped and revisited plane, one that can be scanned repeatedly for the smallest sign of change, through satellites, ground stations, radar waves, and precise positioning. The quiet land begins to show movement that ordinary sight cannot detect. The recent shifts along the two fault lines are not first experienced as a dramatic image on the ground. They appear first as changes in the measurements. A line of numbers that had remained within an expected range begins to depart from that pattern. A new radar comparison reveals a band of displacement where earlier images showed no such change. A cluster of stations anchored in a rock records a small but coherent adjustment in position. Scientists begin with these signs because the surface does not always display a fresh open rupture, and even when it does, the immediate scientific task is to determine what has actually moved, by how much, over what distance, and within what period of time. Measured change can take several forms. In some cases, the ground shifts suddenly during an earthquake, producing abrupt displacement across a fault trace. In other cases, movement occurs more gradually over hours, days, or longer, sometimes without a damaging quake at the surface. This gradual motion is often called slow slip when it happens over a measurable interval rather than in an instant. Whether the recent movement on the two monster fault lines is rapid, gradual, or mixed becomes one of the first questions scientists try to answer from the data. Observations indicate that different segments of the same fault system may behave differently, even during the same general episode of crustal adjustment. A measured shift is described not only by its timing but also by its direction. One side of the fault may move northward relative to the other. It may move slightly upward, downward, or obliquely, combining sideways and vertical motion. These directions matter because they help identify the style of faulting and the stress acting across the region. The movement may align well with the known long-term behavior of the fault, or it may reveal a more complicated pattern involving nearby branches and secondary structures. Scientists compare the observed displacement with older geological and geodetic records to determine whether the recent shift fits an established trend or departs from it. The size of a shift is often smaller than public language suggests. A monster fault line may move by only a modest amount at the surface during a given event. Even though the affected structure extends for a very long distance and has the capacity to release great energy under certain conditions, surface displacement may be measured in millimeters, centimeters, or in some cases larger amounts, depending on the nature of the event. What makes the observation important is not always the absolute size of the motion, but its location, coherence, and relation to other changes across the fault system. A small movement on a crucial segment can matter more scientifically than a larger shift in a less critical setting. Time also matters. Scientists ask whether both fault lines moved at nearly the same time, whether one followed the other after a short delay, or whether both are responding to a broader regional process unfolding over a longer interval. Measurements from satellites, ground stations, and seismic instruments each have their own timing limits. Some data arrive continuously. Some come only when a satellite revisits the region. The sequence must therefore be reconstructed from overlapping observations. This work requires care because apparent simultaneity may reflect coarse timing resolution rather than true physical connection. In other cases, the order of events can be established with much greater confidence. When the recent movement is mapped, scientists look for its spatial extent. Did the shift occur along a short section of each fault, or did it affect many tens of kilometers? Did the displacement remain confined to the known trace, or did it spread across a wider deformation zone with multiple strands moving together? A broad pattern may indicate distributed strain rather than rupture, limited to a single plane. A narrow and sharply defined offset may suggest more localized slip. The geometry of the measured change begins to reveal how the crust responded during the event. Another key issue is whether the motion reaches the surface directly or remains buried at shallow depth. Not all slip on a fault breaks the ground in a visible way. Sometimes the displacement occurs below the surface and is expressed only as gentle warping, subtle strain, or shaking. In such cases, radar interferometry and ground position data may detect the motion even when field teams find little obvious rupture. This is one reason the phrase moved requires careful scientific definition. A fault may have slipped in a mechanically important way without leaving an immediately dramatic surface break. Scientists also examine uncertainty. Every measurement carries limits. Radar scenes may contain atmospheric effects that mimic slight ground movement. GPS time series may include seasonal signals linked to soil moisture, temperature, or other environmental factors. Processing choices can influence the inferred displacement field. Because of this, the most careful interpretations do not announce more precision than the data support. They identify what is firmly observed, what is probable, and what remains unresolved. If the motion on the two fault lines is measured clearly by several independent techniques, confidence increases. If the evidence is weaker or partly conflicting, that uncertainty is stated openly. The public often understands fault movement through the language of danger, but the scientific description remains narrower at this stage. The focus is on the event itself, not yet on the broader field of earthquakes around it or the deeper mechanics beneath it. Scientists determine how far the ground moved, in what direction, across what area, and within what time window. They compare present displacement with the background rate of motion expected in the region. They ask whether the change is unusual for these structures, or consistent with their known behavior over recent years and decades. Sometimes the most revealing feature of a recent shift is asymmetry. One side of a fault may show coherent motion while the other appears comparatively stable. One segment may move while an adjacent segment remains quiet. One of the two major fault lines may show stronger evidence of displacement than the other. Such uneven behavior can indicate that the crust is partitioning strain in a complex way, with some sections slipping while others continue to store stress. Observations indicate that this patchwork behavior is common in real fault systems and is one reason why prediction remains difficult. At this stage, the event remains a measured fact before it becomes a wider interpretation. The land has shifted, the amount is finite, the geometry mappable, the timing reconstructible within limits. Scientists watching closely do so because the measurements show a real change in the state of the fault system. Whether that change represents a minor adjustment, a transfer of stress, a response to nearby shaking, or part of a longer sequence is not yet the question here. The present focus remains fixed on what the instruments and repeated observations actually record. The two monster fault lines, once only traces across a broad landscape and signals in distant data, are now defined by their recent measured motion. The event becomes concrete through displacement fields, position changes, mapped extent, and timing. This is the moment when abstract structure becomes observed change, still described from the outside, still held within the discipline of measurement before the wider surrounding seismic region comes into view. Around the two fault lines, the wider seismic region does not behave as a silent frame surrounding a single event. It has its own pattern of trembling ground, clustered ruptures, quiet intervals, and repeated adjustments that spread across a larger area than the main traces alone. When scientists widen their view from the recent measured shifts to the surrounding field of earthquakes, they begin to see how the region as a whole responds to stress. The main fault lines remain important, but they are now set within a broader zone where many fractures, large and small, contribute to the release and redistribution of strain. An earthquake occurs when stored elastic strain in rock is released suddenly, sending waves through Earth. In the broader region around a major fault, this release does not always happen only on the main mapped structure. Smaller nearby faults may also slip. Some earthquakes occur on short hidden fractures that do not leave a clear trace at the surface. Others cluster near bends, junctions, or stepovers where the geometry of the fault network becomes more complicated. The result is a seismic landscape made of many small and moderate events, punctuated more rarely by larger ones. This pattern gives the region a kind of restless background motion, even during periods when no major rupture is visible. When scientists study the broader seismic setting around two monster fault lines, they begin by mapping where earthquakes occur. Each event has a location, a depth estimate, and a magnitude, which is a measure of the size of the seismic waves generated and the energy released. These locations are not perfectly exact, but taken together they show trends. Earthquakes may line up along the known trace of a fault. They may form clouds to one side of it. They may concentrate in a narrow band at one segment and spread diffusely across a wider area elsewhere. Such patterns help reveal which parts of the crust are actively deforming. After a notable fault movement, scientists often watch for aftershocks. An aftershock is a smaller earthquake that follows a larger event in the same general region, as the crust adjusts to a new distribution of stress. Aftershocks are common, but they do not occur in a simple or uniform way. Their number, spacing, and duration vary widely. Some sequences fade quickly, others continue for weeks, months, or longer. Around the two fault lines, the pattern of aftershocks can show whether the recent motion was concentrated in one area or whether it disturbed a broader part of the fault system. A dense cluster of smaller events may indicate ongoing adjustment near the slipped segment, while a more scattered pattern may suggest stress changes across a wider network of fractures. Not all nearby earthquakes are aftershocks in a strict sense. Some may be part of an ongoing background rate of seismicity that predates the recent movement. Others may be triggered in a looser way by stress transfer, where changes caused by one slip episode make failure slightly more likely on neighbouring structures. Scientists distinguish these possibilities carefully because the broader region is never completely still, even in ordinary periods. Many faulted areas produce small earthquakes too weak to be felt by most people. Sensitive instruments detect them and add them to long catalogues of regional seismicity. These catalogues become one of the main tools for understanding the surrounding region. By comparing the number, size, and distribution of earthquakes before and after the recent movement, researchers can ask whether the fault system is behaving differently from its usual pattern. A temporary increase in small events near one segment may indicate local adjustment. A migration of activity along strike, meaning along the length of the fault, may suggest that stress is being reorganized over distance. In some cases, seismicity appears to move outward from the main area of slip. In others, it remains tightly concentrated. Observations indicate that no single pattern applies to all fault systems, and careful regional analysis is always required. Depth is also important, even while the focus remains on the broader seismic region rather than the deeper mechanics of the fault interior. Earthquakes in the surrounding area often occur within the brittle part of the crust, where rock is cool and strong enough to fracture suddenly rather than flow slowly. Some events cluster at shallow depths, others occur several kilometers below the surface. The depth range can help scientists identify which structures are active and whether the recent movement affected only the shallow crust or influenced a thicker seismogenic zone. The seismogenic zone is the portion of the crust where earthquakes commonly nucleate because brittle failure is possible there. The wider seismic field also includes areas of relative quiet. These quiet stretches matter because they may indicate segments that are creeping without much seismic release, or segments that are locked and accumulating strain without frequent small earthquakes. Silence is not always reassuring. In some contexts, low seismicity can simply mean that a fault is not releasing stress through many small events. In others, it may reflect limited instrumentation or poor detection in remote terrain. Scientists therefore interpret quiet patches cautiously, comparing them with geodetic measurements and geological evidence rather than assuming a single explanation. Regional stress helps organize these patterns. Stress in this context refers to the forces per unit area acting within the rock. In a tectonically active region, stress is imposed by large-scale plate motion and modified by local structures, rock properties, and past earthquakes. When one fault slips, it can increase stress on some nearby faults and decrease it on others. This process, often modelled mathematically, does not determine with certainty what will happen next, but it helps explain why clusters of earthquakes may appear in some places after a shift, while other areas remain quiet. Scientists use these models carefully because the crust is complex and real behavior does not always follow the simplest expectations. The surrounding seismic region may also include swarms, which are clusters of earthquakes without one clearly dominant main shock. Swarms can occur near active faults, volcanic areas, or places where fluids move through fractured rock. If a swarm appears near one of the two major fault lines after recent movement, it draws attention, but its significance is not always obvious. It may represent local adjustment on minor fractures. It may reflect fluid effects in damaged rock. It may be only loosely connected to the main event. In such cases, scientists describe the observations clearly while avoiding stronger conclusions than the data allow. Felt shaking across nearby communities becomes part of the regional picture as well. Though human experience is not the primary measure used in scientific assessment, reports of shaking can help identify the distribution of ground motion, especially when combined with instrumental data. Some areas may experience repeated small jolts, while others feel little despite being close to the main fault. Local geology influences this strongly. Soft sediments can amplify shaking, while hard bedrock may transmit it differently. Even so, the scientific emphasis remains on the regional pattern of seismic sources, not yet on the shallower materials that modify surface effects. Viewed at this scale, the two monster fault lines no longer stand alone. They are embedded in a living seismic region that includes main traces, subsidiary fractures, clustered earthquakes, aftershocks, swarms, quiet gaps, and changing stress conditions. The recent movement is one part of this larger field of adjustment. The crust around the faults responds unevenly, with some areas slipping, some fracturing, and some remaining outwardly still. The map of the region grows denser as each small earthquake adds another point, another hint of how strain is distributed around the main structures. The broader seismic environment therefore becomes the immediate outer ring surrounding the shifted faults. It is not yet the rock fabric at the surface, nor the sediments, water, or instruments placed nearby. It is the active earthquake field within which the two faults exist, a region where motion is recorded not only in displacement measurements, but in repeated pulses of seismic release across space and time. Near the surface, the crust stops looking like a broad moving region and begins to appear as material with texture, grain, layering, and damage. The two fault lines, which from far away seem like long marks across the land, are at close-range zones of broken rock. Their presence is written into outcrops, ridges, gullies, scarps, and shattered layers that no longer sit in their original positions. This is the fractured skin of the crust, the outermost rock record of repeated movement. It is here that scientists read the physical traces left behind by stress and slipping, not as abstract measurements but as changes fixed into stone and soil. Surface rocks vary from place to place along a fault. One segment may cut through hard crystalline bedrock formed deep in earth long ago and later exposed by uplift and erosion. Another may pass through layered sedimentary rock, once laid down in rivers, lakes, deserts, or shallow seas. Another may intersect volcanic deposits, loose alluvium, or old landslide material. The fault does not require one special type of rock. It cuts whatever lies in its path. Yet the way a fault appears at the surface is strongly shaped by the material it crosses. Hard rocks may preserve sharper scarps and cleaner exposures. Softer deposits may deform more diffusely, developing cracks, folds, and subtle warping instead of one narrow break. In outcrop, repeated fault motion often produces a rock fabric marked by crushing and shearing. Shearing refers to deformation caused when adjacent parts of a material slide past one another. Along a fault zone, this can grind strong rock into angular fragments or finer clay-rich material. The resulting zone may be visibly different from the rock around it. Layers become truncated. Mineral grains are stretched, rotated, or broken. Sharp contacts between rock types may be offset. Veins that once crossed an outcrop in a straight line may be displaced so that one segment no longer meets the other. Even a small exposure can show the signature of a much larger structure. Fault scarps are among the clearest surface expressions of recent or repeated motion. A scarp is a step-like slope or small cliff where one side of the ground has moved relative to the other. In some settings, a fresh scarp appears crisp, with bare soil or exposed rock marking the break. In other places, it becomes softened over time by weathering, plant growth, and sediment accumulation. A fault scarp need not be dramatic to be important. A rise of less than a meter can still indicate meaningful displacement if it extends consistently along the trace. Scientists study the shape, continuity, and freshness of scarps to estimate whether motion is recent and whether multiple events may be recorded in stacked or modified forms. Cracks and fissures near the fault can form during or after movement, but not all cracks mark the main fault plane itself. Some open because the ground bends or stretches adjacent to the principal slip zone. Others reflect shaking, slope failure, or settling in loose surface material. For this reason, the fractured surface around a major fault often includes a family of features rather than one simple break. En echelon fractures, which are short, overlapping cracks arranged obliquely in a repeated pattern, may appear where the ground is being sheared near the surface. These structures help scientists infer the direction of movement. Their geometry acts like a small-scale indicator of the broader tectonic motion. Offset layers provide some of the strongest evidence that a fault has moved repeatedly. A gravel bed deposited long ago on one side of the fault may be shifted sideways or vertically relative to its continuation on the other side. A volcanic ash layer, once spread widely across the landscape, may now sit at different elevations across the trace. Ancient stream deposits may be cut and displaced so that their former geometry can be reconstructed. These offsets are especially useful when the age of the material can be estimated, because they allow scientists to compare the amount of motion with the time over which it occurred. At the close surface scale, the fault becomes a place where the history of movement is layered into the ground itself. Broken rock near a fault is not distributed evenly. There is often a core zone where deformation is most concentrated, surrounded by a broader damage zone in which fractures become more numerous than in the surrounding crust. In the damage zone, joints may open, small faults may branch, and rock strength may be reduced. A joint is a crack in rock with little or no visible displacement across it. Around major faults, dense networks of joints and fractures can weaken slopes, redirect water, and influence erosion. The landscape then begins to reflect not only the primary fault trace, but also the mechanical effects of the damaged rock around it. Weathering works constantly on these fractured materials. Rainwater enters cracks and helps widen them. Temperature changes cause expansion and contraction. Plant roots grow into openings. Over time, the broken zone may erode faster than the more intact rock on either side, creating linear valleys or notches that follow the fault trace. In other settings, resistant rocks within the faulted terrain may stand out as aligned ridges. The resulting landform does not come from tectonics alone. It is the product of tectonic damage plus weathering and erosion acting on that damage over many years. The close study of surface rocks also reveals that many fault zones record more than one style of motion. A polished rock surface may show parallel grooves called slicken sides, produced when one wall of the fault scraped against the other. These grooves indicate slip direction. Nearby, folded or dragged layers may suggest compression or tension superimposed on sideways movement. Small subsidiary faults may cut older ones at different angles, preserving a sequence of changing conditions across time. The fault line at the surface is therefore not a single frozen moment. It is a palimpsest of repeated deformation, with newer motion written over older signs but not always erasing them completely. When scientists investigate the two monster fault lines after recent movement, they look closely at these materials and structures. They search for fresh rupture in road cuts, stream banks, bare hillsides, and trench walls. They compare newly opened cracks with older weathered fractures. They examine whether broken rock is sharply localized or spread across a broad corridor. They note whether displaced layers match the expected style of motion from instrument data. Field evidence of this kind is especially valuable because it ties remote measurements back to real material change in the crust. Uncertainty remains even at this intimate scale. Surface fractures can be modified quickly by rainfall, traffic, farming, or cleanup activity. Some breaks that appear fresh may reflect slope failure rather than fault slip. In vegetated or urban terrain, important traces may be hidden, A segment may have slipped below the surface with only subtle warping above it. For these reasons, the fractured surface is interpreted carefully and in context. No single crack proves the whole story, but together the rocks, scarps, offsets, and damage zones form a coherent record. At this level, the fault is no longer just a line on a map or a pattern in remote data. It is broken stone, shifted layers, crushed zones, and fractured ground close enough to touch. The two major faults are read through their surface materials, where strain has left its first direct signature in the outer skin of the crust. Around a major fault, rock is only part of the surface story. Over that rock lies a shifting cover of sediment, soil, river gravel, lake mud, wind-blown dust, and groundwater moving slowly through pores and fractures. These materials are softer, younger, and more easily altered than the bedrock below. They do not create tectonic forces, yet they strongly influence how fault motion appears at the surface and how its traces are preserved or erased. Along the two monster fault lines, this layer of loose material becomes a delicate record of movement, one that can sharpen the evidence in some places and almost conceal it in others. Sediment gathers wherever water, wind, gravity, and ice transport broken material from higher ground to lower ground. Rivers carry sand, silt, pebbles, and larger stones into valleys. Floods spread thin sheets of mud across plains. Alluvial fans, which are broad cone-shaped deposits formed where streams leave steep terrain and slow down, build outward at the edges of mountains. In closed basins, fine particles settle through still water to form layered muds. Wind lifts dust from dry surfaces and spreads it across wide regions. Over time, these materials bury older landscapes and create new surfaces across which faults continue to move. When a fault cuts through loose sediment, its expression often differs from what appears in strong bedrock. Instead of a single clean fracture, the surface may warp, crack in several parallel strands, or deform across a broader zone. Saturated ground can slump or spread during shaking. Soft layers may absorb some of the strain and distribute it unevenly. A recent movement therefore may appear as a small scarp in one patch of gravel, a set of tension cracks in another, and only subtle bending a short distance away. The same fault event can leave very different signatures depending on the sediment present at the surface. River systems are especially sensitive to fault motion. A stream crossing an active fault may have its channel offset sideways, lifted, lowered, or redirected by even modest ground deformation. Over repeated episodes, these changes accumulate into a geomorphic record. A geomorphic record is the history of physical landscape change preserved in landforms. Terraces, which are old abandoned floodplain levels left above the modern river, may be shifted across the fault. Channels may bend sharply where they cross the trace. Ponds may form in small depressions created by local extension within a sideways moving fault zone. Such features are often among the clearest markers that fault movement has continued into the recent geological past. Water moving through sediment also interacts closely with fractured ground. Fault zones can either block groundwater flow or channel it. If clay-rich fault gouge forms a barrier, water may collect on one side, changing soil moisture and plant growth. If fractured material creates open pathways, groundwater may rise along the fault and feed springs, wetlands, or persistently damp ground. These differences matter because they can reveal the fault's position even where the surface break itself is obscure. A linear band of greener vegetation in an otherwise dry landscape may reflect groundwater, concentrated along a damaged zone in the crust. Heavy rain and repeated flooding can quickly alter the surface expression of a recent shift. A fresh scarp cut into a stream bank may be softened or partly removed within a season. Sediment washed from upslope can fill small fissures and level tiny steps in the ground. Fine mud deposited during floods may blanket a rupture trace and preserve it beneath the new surface, while hiding it from immediate view. In this way, erosion and burial act together. One removes evidence from sight, while the other protects it within the subsurface. Scientists studying active faults therefore pay close attention not only to what is visible now, but also to what may be preserved just below the present ground. Dry regions preserve faulted landforms differently from wet ones. In arid landscapes, sparse vegetation and limited runoff often allow scarps, offset channels, and linear depressions to remain visible for long periods. Wind may move fine dust, but the general shape of the ground can stay legible for centuries or longer. In wetter climates, abundant plant cover, slope wash, landslides, and soil formation may obscure the same kinds of features much faster. A fault that is obvious in a desert may be nearly hidden in a humid valley. The difference does not reflect weaker tectonic activity. It reflects how surface processes rewrite the uppermost record. Sediment thickness matters as well, where only a thin blanket of soil covers bedrock. Fault motion may break through clearly and reveal the underlying structure. Where young deposits are thick, the recent history of the fault may be recorded mainly within those deposits rather than in the bedrock below. This is one reason trench studies often target river terraces, alluvial fans, and basin sediments. These materials can preserve layers that are datable and deformable, allowing scientists to see how past earthquakes and slips disturbed the shallow ground. Though trenching belongs more to the tools of observation, the materials themselves are part of this sedimentary layer and its ability to record disturbance. Groundwater adds another level of complexity during and after seismic movement. Shaking can change pore pressure, which is the pressure of water held within the spaces between grains. If pore pressure rises in loose saturated sediment, grain-to-grain contact weakens, and the material can temporarily lose strength. In extreme cases, this may contribute to liquefaction, a process in which water-rich sediment behaves more like a fluid during intense shaking. Sand blows, lateral spreading, and ground settlement may then appear near the fault or in nearby basins. These effects do not define the main tectonic slip, but they become part of the shallow environmental response that scientists must distinguish from the principal fault rupture. Even in the absence of strong shaking, the slow movement of water helps shape fault landscapes over long intervals. Springs deposit minerals. Wet ground encourages organic accumulation. River incision exposes older displaced layers. Seasonal saturation and drying alter slope stability and soil cohesion. Each of these processes changes how the fault trace appears. A fault crossing a broad alluvial plain may be expressed only as a slight rise, a subtle moisture contrast, or a line of altered drainage. Another segment crossing a deeply incised valley may be exposed dramatically in cut banks and terrace walls. The underlying tectonic boundary remains the same, but the sedimentary environment controls what can be seen. Scientists watching closely after movement on two major fault lines therefore study the surface cover with as much care as the bedrock. They examine displaced stream channels, fresh cracks in floodplain deposits, ponded water in new depressions, changes in spring flow, and subtle warping across young sediment. They compare what the sediment says with what the instruments record. In some places, the loose material confirms the measured motion clearly. In others, it complicates interpretation, masking the trace or producing secondary effects that must not be mistaken for the main slip. At this layer of the crust, the fault passes through moving water, drifting grains, and easily altered ground. The rigid image of a fault as a clean break in stone gives way to something softer and more changeable. Sediment and groundwater receive the motion, reshape its evidence, and decide how much of the recent shift remains visible at the surface. The outer broken rock is now covered by this living layer of transport, burial, erosion, and moisture, where the fault's history is both preserved and concealed. Close to an active fault, the landscape becomes not only a record of past motion, but also a place of constant listening. Instruments are placed on hillsides, in valleys, beside roads, near exposed scarps, and above buried traces in sedimentary basins. Some are anchored directly into bedrock. Others are installed in shallow boreholes or beneath protective covers that shield them from weather. Around the two monster fault lines, these devices form a monitoring network. A human attempt to remain attentive to a crust that moves too slowly for ordinary sight and too suddenly for ordinary reaction. This is the zone where the surface environment gives way to deliberate observation at close range. One of the most familiar tools is the seismometer. A seismometer is an instrument that detects ground motion, including vibrations far too small for people to feel. In its basic purpose, it records how the ground moves with time. When an earthquake occurs, waves travel outward through the crust and cause the instrument to respond. The resulting record shows the arrival of different kinds of waves, their amplitude, and their duration. From many such records across a region, scientists estimate earthquake location, depth, and size. Near a major fault, dense arrays of seismometers can detect very small earthquakes that broader national or global networks might miss. These tiny events matter because they reveal where the crust is fracturing, adjusting, or slipping quietly. A single seismometer can only tell part of the story. A network is needed because the location of an earthquake is found by comparing arrival times at multiple stations. If the network is sparse, the location may be uncertain by several kilometers or more. If the network is dense and well placed, the earthquake can be located much more precisely, along active fault lines. Scientists often try to reduce this uncertainty because even small differences in position can determine whether a cluster lies on the main fault trace, on a subsidiary fracture, or within the surrounding damaged crust. Precision at this scale helps connect seismic activity to the mapped structures at the surface. Another close-range tool is the strain meter. A strain meter measures very small changes in the deformation of rock or soil between 2 points. Strain in this sense refers to the change in shape or length of a material caused by stress. Some strain meters are installed in boreholes to shield them from surface noise such as temperature changes, rainfall effects, and human activity. These instruments can sometimes detect gradual deformation that happens before, during, or after small fault movements. They are especially valuable where slow slip or creeping motion may occur, because such motion does not always produce a strong seismic signal. A fault can move measurably while remaining relatively quiet in terms of earthquakes, and strain instruments help reveal that hidden behavior. Ground position measurements continue at close range as well. Permanent GPS stations remain important, but scientists may also install temporary receivers after a notable shift. These may be placed strategically across a fault to capture how deformation evolves in the following days, weeks, or months. In some regions, robotic total stations and corner reflectors are used to measure line-of-sight changes repeatedly across the trace. A total station is an optical surveying instrument that measures angles and distances with high precision. Though more limited in area than satellites, Such ground-based methods allow focused monitoring of a specific segment where recent movement has drawn attention. Field surveys remain central in this observational region. Scientists walk the trace, flag fresh cracks, measure offsets in channels and roads, and inspect scarps with tapes, rods, and precise leveling equipment. Drones may fly low over the area to create detailed surface models from overlapping photographs. These models help reveal centimeter-scale features that are difficult to appreciate fully from the ground. When combined with direct measurements, they allow researchers to map the shape and extent of rupture in great detail. The work is patient. A small offset in a fence line, a narrow fissure in an alluvial fan, or a subtle rise in a farm track may all carry valuable information when placed into a larger map of deformation. One of the most revealing tools near an active fault is the trench. In paleoseismology, which is the study of ancient earthquakes preserved in geological records, a trench is excavated across the fault trace to expose layers of sediment and soil beneath the present ground. These layers may show breaks, tilting, folding, or abrupt terminations caused by past fault movement. Organic material, volcanic ash, or other datable layers can sometimes be used to estimate when those movements occurred. In the immediate aftermath of a recent shift, trenches may help determine whether fresh deformation connects with older events at the same site. They also show whether the fault breaks the surface repeatedly in a similar way, or varies from one event to another. Creep meters are another close-range device sometimes used where faults are known to move slowly at the surface. A creep meter spans the fault with a wire rod and records very small changes in the distance between anchor points on opposite sides. If one side shifts gradually relative to the other, the instrument captures that motion through time. Not every fault segment is suitable for such monitoring, and the instrument is limited to a very local span. But where surface creep occurs, it can provide a clear record of steady or episodic movement. This helps scientists distinguish between segments that slip gradually and those that remain locked for longer intervals. The near-fault environment also contains sources of noise that complicate measurement. Wind can shake poorly sheltered equipment. Rain alters near-surface conditions. Temperature expansion affects exposed hardware. Passing vehicles, industrial activity, and construction can introduce vibrations into seismometer records. Groundwater changes can influence shallow deformation measurements. For these reasons, site selection matters greatly. Instruments are placed where the signal of tectonic motion can be separated as much as possible from environmental disturbance. Even then, interpretation requires care, and no reading is accepted without considering alternative explanations. Monitoring networks do more than record the main event. They reveal the continuing life of the fault zone before and after obvious movement. Small repeating earthquakes may appear on one patch of the fault, suggesting repeated failure on a limited asperity. An asperity is a small, stronger or more resistant part of a fault surface that can remain stuck while surrounding areas behave differently. Strain may continue to evolve after the principal shift, showing post-seismic adjustment in the crust. Seismicity may migrate along the fault or into nearby structures. Ground position may settle into a new trend. These ongoing observations are what turn a fault movement from a single event into a documented process. Scientists watching the two monster fault lines closely do not rely on one instrument or one visit to the field. They build layered monitoring systems, each one sensitive to different forms of motion. Seismometers listen for fracture and wave energy. Strain meters detect subtle deformation. GPS receivers track position. Drones and survey crews map surface change. Trenches expose the hidden record just below the ground. Together, These tools bring the focus inward from the broader sedimentary cover to the deliberate points of measurement placed directly within the active zone. At this stage, the fault is surrounded by observers, both human and mechanical. The ground is not only broken and water-shaped, it is instrumented. Every slight shift becomes a potential signal. Every small quake becomes a data point. The close surface region is now defined by its monitoring network, which watches the fault not from far above but from within its own immediate terrain. Beneath the instrumented ground and the young cover of sediment, the shallow crust appears as a mosaic of rock blocks that do not move as one continuous mass. These blocks vary in size, shape, strength, and internal structure, yet they are joined within a faulted region by the stresses that pass through them. The two monster fault lines are not empty cracks cutting through still material. They are boundaries within a shallow crust that bends, stores strain, creeps in places, locks in others, and transfers motion from one block to the next. At this level, the fault system is no longer defined mainly by what can be seen at the surface. It is defined by how the upper crust is partitioned into moving pieces. A crustal block is a body of rock that behaves somewhat coherently relative to neighbouring blocks over a given interval of time. It is not perfectly rigid in the strictest sense, because all rock deforms to some degree under stress. Still, at the scale of a major fault network, some sections of the upper crust move in a way that allows scientists to treat them as blocks with measurable boundaries and relative motion. One block may drift slowly northwestward, another may rotate slightly. Another may rise while also shifting sideways. The fault lines between them accommodate these differences, either by steady creeping, repeated small earthquakes, larger intermittent ruptures, or some mixture of all three. The shallow crust in an active fault zone is usually brittle. Brittle means that rock under stress tends to fracture rather than flow smoothly. This behaviour dominates in the cooler upper levels of the crust, where pressure is not yet high enough and temperature is not yet great enough for widespread ductile deformation. Within this brittle shell, pre-existing fractures matter greatly. Old faults, joints, bedding planes, and intrusive contacts all influence how stress is distributed. When scientists examine the region around two recently shifted fault lines, they often find that the motion is not confined to one perfect plane. Instead, the surrounding crust responds through a network of faults and damaged blocks that share the load unevenly. Some blocks remain relatively intact between major structures. Others are broken internally by many subsidiary faults. A subsidiary fault is a smaller fault connected mechanically or geometrically to a larger one. Where subsidiary structures are abundant, the shallow crust may deform across a wider zone rather than along one narrow boundary. This broad deformation can produce distributed strain, meaning that neighbouring blocks each absorb part of the relative motion. In such regions, the crust behaves less like two clean slabs sliding past one another, and more like a crowded arrangement of imperfect pieces adjusting together under pressure. Within this broken upper crust, one of the most important distinctions is between locked behaviour and creeping behaviour. A locked segment is one where friction and normal stress keep the opposing sides of a fault from slipping freely at the present time, even though tectonic forces continue to push or pull on the region. As a result, strain builds in the surrounding rock. A creeping segment, by contrast, slips gradually without storing as much elastic strain over long intervals. The shallow crust around a major fault can include both kinds of behaviour at different places and times. One block boundary may glide slowly, while another nearby remains stuck and accumulates stress. Observations indicate that such contrasts are common and help explain why fault systems behave irregularly. Elastic strain within the blocks becomes crucial here. Elastic means that material deforms under load but tends to return toward its earlier shape if the load is removed, at least until failure occurs. In the shallow crust, tectonic forces slowly distort rock blocks around locked fault segments. The deformation may be extremely small at any moment, far below ordinary perception, yet over years and decades it becomes measurable. GPS networks and radar data reveal this slow bending and compression of the crustal blocks even when no surface rupture occurs. The blocks do not remain perfectly rigid. They flex under stress, storing energy that may later be released suddenly if the locked segment fails. Block motion is also influenced by geometry. A fault that bends, branches, or steps sideways creates local complications in how neighbouring crustal pieces move. In a releasing bend, where the geometry encourages local extension, blocks may subside or rotate slightly as the crust opens. In a restraining bend, where the geometry imposes compression, blocks may uplift, shorten, or become more strongly fractured. These local conditions can affect whether a segment creeps, locks, or breaks in earthquakes. The recent movement of two large fault lines is therefore understood partly through the shapes of the shallow crustal blocks around them. The architecture of the block mosaic guides the path of strain. Not all blocks respond immediately when a neighbouring fault slips. Some may remain temporarily quiet, carrying stress with little outward sign. Others may experience a change in motion soon after a nearby event. A block caught between two major fault strands may rotate slightly as stress redistributes. Another may act as a relatively strong buttress, resisting motion and forcing deformation into adjacent weaker zones. These variations matter because they help determine where future slip is mechanically easier or harder, even when the present focus remains on the shallow crust. The system already shows that movement is shared unequally among the pieces. The material properties of the blocks further complicate the picture. Some upper crustal rocks are massive and competent, meaning they are mechanically strong and resist deformation until stress becomes high. Others are layered, altered, porous, or already intensely fractured, making them more compliant and easier to deform. A compliant block may absorb strain more gradually, or distribute it across many small structures. A stronger block may remain more intact while focusing stress at its edges. Thus the two fault lines do not cut through a uniform crust. They mark boundaries through a patchwork of blocks with differing strengths, histories, and internal damage. Shallow crustal blocks also carry the imprint of past earthquakes and older tectonic episodes. Ancient fractures may be reactivated if they are favourably oriented within the current stress field. Older damage zones may localize modern strain because broken rock is mechanically weaker than intact rock. A block that appears simple from the surface may contain inherited structures that influence how it behaves under present loading. Scientists studying the recent shifts therefore compare new deformation patterns with the mapped fabric of the shallow crust. If motion aligns with older structures, that suggests the crust is reusing established weaknesses rather than creating entirely new pathways. Even where no earthquake has just occurred, block boundaries may move through small episodic adjustments. Tiny seismic events, shallow creep, and subtle geodetic changes all point to a crust that is never fully motionless. The difference between apparent stillness and true mechanical activity becomes clear at this level. What seems to be solid ground is actually a collection of shallow crustal pieces under continuous but uneven stress. The fault lines matter because they organize this stress, but the blocks on either side are active participants, bending and shifting in response. For scientists watching closely after movement on two major faults, understanding these shallow blocks is essential. The recent shift is not only a matter of what happened on the main traces, it is also a question of how the surrounding crust accommodates and transmits that motion. Which blocks moved together, which bent elastically, which rotated slightly, and which remained comparatively stable all shape the interpretation of the event. The shallow crust is therefore the first true interior layer of the system, no longer just surface expression, but still within the brittle upper shell where blocks and boundaries interact directly. At this inward stage, the fault zone becomes a mechanical landscape of crustal pieces. The surface traces remain above, but below them lie the shallow blocks that lock, creep, flex, and transmit tectonic motion. The two monster fault lines cut through this mosaic, and their recent movement can only be fully understood as part of the larger behavior of the upper crust that surrounds them. Within the shallow crustal blocks, the fault itself narrows into a boundary where opposing rock surfaces come into contact. At this scale, the vast landscape, the sediment cover, and even the mosaic of moving blocks give way to the physical meeting place where one side of the crust presses against the other. The motion of a fault depends not only on the large forces acting across a region, but also on the small-scale behavior of this contact. Here, the central process is friction. The resistance to sliding that arises when two surfaces press together and attempt to move past one another. A fault plane is not usually a smooth geometric sheet. Even when drawn that way on diagrams, the real surface is rough, irregular, and marked by ridges, bumps, crushed zones, and patches of finer material. These irregularities matter because they control how strongly the two sides grip each other. Some parts of the plane may be held tightly where rough projections interlock. Other parts may contain finer fragments or mineral coatings that allow easier sliding. The overall behavior of the fault is therefore the combined result of many small contacts rather than one perfectly even surface. Friction on a fault begins with the normal force, which is the force pressing the two sides together. Greater normal force usually means greater resistance to sliding, because the rock surfaces are held in tighter contact. At shallow depths, this force is influenced by the weight of overlying rock and by local tectonic compression. Even a fault that is favorably oriented for movement may remain stuck if the normal force and the surface roughness together create enough resistance. This is why large tectonic stresses can build over time without immediate slip. The rocks are being pushed, but the frictional barrier has not yet been overcome. The roughness of the fault plane is often described in terms of asperities. An asperity is a stronger or more protruding patch on the fault surface where the two sides make firm contact. These patches can act like anchors. Surrounding parts of the fault may be weaker or more ready to slip, but the asperity holds the system in place until stress rises high enough for failure or for surrounding areas to adjust around it. In a long fault zone, asperities are not evenly distributed. Some segments may be dominated by larger or more persistent locked patches, while others contain fewer barriers and can slide more readily. This uneven arrangement helps explain why motion along major faults is irregular in space and time. When sliding begins, the fault may not behave in a simple all-or-nothing way. In some cases, there is stick-slip behavior. This means the two sides remain stuck while stress accumulates, then suddenly slip when frictional resistance is exceeded, only to stick again afterward. This behavior is associated with many ordinary earthquakes. In other cases, the fault may creep, meaning it slides gradually and more continuously without a large sudden release. Between these end members lies a wide range of mixed behavior. A fault may creep in one patch, lock in another, and undergo small episodic slips elsewhere. Observations indicate that real fault systems often contain all of these behaviors at once. The state of the material along the fault plane also affects friction strongly. If the boundary contains coarse angular fragments, the surfaces may jam and resist motion. If the material has been ground into very fine clay-rich gouge, sliding may become easier under some conditions. Certain minerals absorb water or change their mechanical behavior when wet, altering the strength of the fault zone. Other minerals may become polished by repeated slip, creating smoother surfaces locally. These details are small compared with the length of the two monster fault lines, yet they influence whether a given section remains locked, slips quietly, or ruptures suddenly. Friction is not fixed. It changes with slip rate, temperature, pressure, surface condition, and the history of contact. One important concept is that a fault may weaken once slip begins. This means that the force needed to keep the fault moving can be lower than the force needed to start the motion. If weakening happens quickly, rupture can accelerate and spread. If strengthening occurs with motion, sliding may slow or stop. Scientists describe these tendencies with experimental friction laws developed from rock mechanics, but the essential idea remains simple. A fault is not merely either stuck or free. Its resistance evolves as conditions change during contact. Even before large rupture occurs, tiny local failures can happen on the fault plane. Small contact points may break, reform, and break again. These microscopic adjustments can generate small earthquakes or contribute to slow deformation. The fault surface is therefore active even during periods that seem quiet at larger scales. Under sustained tectonic loading, the contact boundary continually tests its own resistance. Some patches give way gently, others hold. The overall motion of the fault emerges from this competition between loading and resistance across many scales. Where the fault bends or changes orientation, frictional conditions can shift sharply. A bend that brings the two sides into stronger compression may increase contact and make sliding more difficult. A bend that slightly reduces compression may create a patch where slip is easier. Stepovers and branching structures also change the local stress field along the plane. For this reason, friction cannot be understood only as a property of rock type. It must be understood in relation to geometry. The shape of the fault influences how tightly its walls press together and how its rough patches are loaded. Fluids present along the fault can reduce effective normal stress, which is the portion of the normal force truly carried by grain-to-grain contact rather than by pore fluid pressure. If fluid pressure rises within the fault zone, the rocks may be pushed apart slightly at the microscopic level, reducing frictional resistance. This does not mean the fault becomes frictionless. It means the same tectonic stress may be more able to produce slip at the present stage. The focus remains on friction itself. So the deeper source and chemistry of fluids are not yet central. Still, their mechanical effect at the contact boundary must be acknowledged because it can alter whether a patch sticks or slides. When scientists watch two major fault lines after recent movement, they often ask whether the observed slip occurred on a relatively weak segment, whether a locked asperity failed, or whether creep on one patch transferred load to another. These questions arise because surface measurements alone cannot explain the pattern fully. The physical character of the fault plane must be considered. A short section may slip repeatedly because its frictional resistance is low. Another may remain motionless for long intervals because roughness, normal stress, and material properties keep it locked. The recent motion is therefore a surface expression of conditions at this narrow sliding boundary. The contact between fault walls also leaves clues. Slicken sides, polished surfaces, mineral smears, crushed gouge, and repeated fracture sealing all record earlier episodes of sticking and slipping. These features show that friction is not an abstract idea imposed from outside. It is written directly into the material history of the fault. Every prior event modifies the surface that will govern the next one. A fault plane is shaped by its own memory. It carries forward the effects of past loading, past rupture, and past mineral change into future behavior. At this inward layer, the broad tectonic story narrows to the place where motion is either resisted or allowed. The two monster fault lines become surfaces of contact, rough and changing, where friction governs whether the crust remains stuck or begins to slide. The blocks above and around them still matter, but here the decisive question is physical resistance along the fault plane itself, where Earth's crust meets its own boundary and struggles against motion. Beneath the rough contact of the fault plane, the question of motion becomes a question of stored force within rock. Friction explains why opposing sides resist sliding, but friction alone does not describe what is building around that resistance. The surrounding crust is being loaded continuously by tectonic motion. As long as the fault does not slip freely enough to release that motion at the same rate, the rock around it changes shape slightly and stores energy. This stored condition is called stress. Stress is the force acting within a material over a given area, and in a faulted crust it is not spread evenly. It gathers, shifts, concentrates, and relaxes in patterns that depend on the geometry of faults, the strength of rocks, and the history of earlier events. A rock mass under tectonic loading does not usually fail at once. It first deforms. In the brittle upper crust, much of this deformation is elastic up to a limit. Elastic means the material changes shape under load, but tends to return toward its earlier form if the load is removed before breaking occurs. In the region around a locked fault segment, this elastic strain accumulates gradually. The term strain refers to the change in shape, length, or angle produced by stress. It may involve shortening, extension, bending, or shear. Along major sideways moving faults, shear strain is especially important because neighbouring blocks are being forced to move past one another while the fault itself may still be stuck. The amount of deformation stored in this way is usually extremely small at any one moment, far below what ordinary human senses can detect. A landscape can seem completely still while its rocks are being bent by tiny fractions, yet over years, decades, and centuries, these small increments matter. Survey instruments, satellite positioning, and precise strain measurements show that the crust around major faults is often under steady loading. If a segment remains locked, the neighbouring rock is slowly distorted as tectonic motion continues. This distortion is the outward mechanical sign that stress is building, even if no rupture has yet occurred. Stress in rock is not a single simple quantity. It has direction as well as magnitude. One part of the crust may be under compression, where material is pushed together. Another may be under extension, where it is pulled apart. Near major strike-slip faults, shear stress, which tends to drive sideways motion, becomes especially important. The total state of stress at any point reflects the combined influence of overlying rock weight, regional tectonic forces, nearby faults, bends in the fault trace, and changes left behind by earlier earthquakes. The result is a complex field rather than a uniform pressure acting equally in all directions. A locked fault segment acts like a barrier within this field. Tectonic forces continue to push on the crust, but because sliding is resisted, the surrounding rock takes up the mismatch. One side may be dragged slowly forward while still held in place at the contact. The other side does the same in the opposite sense, strain accumulates around the boundary, and elastic energy is stored in the deformed rock. This stored energy is often compared to a bent branch or a stretched spring, not because the crust behaves exactly like those objects, but because the comparison captures the essential idea. Material under strain is holding potential for motion if resistance is overcome. Scientists attempt to estimate where stress is accumulating by observing deformation at the surface and by modeling the crust beneath. They do not measure stress directly over wide regions in the same simple way they measure position, but they infer it from how the crust is changing shape and from the mechanical properties of the rocks involved. If GPS stations on opposite sides of a fault move at different rates while the fault itself does not slip openly, that difference implies accumulating strain. If the pattern of deformation broadens or sharpens through time, it may suggest changes in how stress is being distributed. Such inferences are powerful, but they remain imperfect because Earth's crust is heterogeneous and the deeper state of stress cannot be seen directly. Stress concentration becomes especially important near fault bends, segment ends, and asperities. An asperity, as already defined, is a stronger patch on the fault plane that resists slip more than surrounding areas. Around such a patch, stress may grow higher because neighboring parts of the fault or surrounding rock are forced to accommodate the continued tectonic loading. In some cases, smaller earthquakes occur around the edges of these highly stressed zones. In other cases, the region remains relatively quiet while stress continues to accumulate. Silence does not necessarily mean low stress. It may mean only that the fault is holding. Every earthquake changes the local stress field. When a fault slips, it releases stress in some places while increasing it in others. This redistribution does not spread evenly. One segment may be partly relieved, while a neighboring one is brought closer to failure. This is one reason scientists monitor two recently shifted fault lines so carefully. Movement on one structure may alter the stress carried by the other, even if the two do not rupture together. The change may be small, but in a crust already near failure on some segments, even modest stress adjustments can matter. Observations indicate that stress transfer helps explain some earthquake sequences, though it does not provide certainty about what will happen next. The strength of the surrounding rock influences how much stress can build before failure. Stronger rocks may store more elastic strain before breaking. Weaker or more fractured rocks may localize deformation earlier and distribute it across many small structures. Temperature, fluid pressure, rock fabric, and mineral composition all play roles. Even within the same fault zone, one patch of crust may respond differently from another because its material properties are not identical. For this reason, the buildup of stress is patchy. It is shaped not only by the external tectonic forces but also by the internal character of the rocks receiving those forces. Time is central to this process. Stress accumulation does not move at the pace of weather or ordinary human attention. It unfolds over long intervals, often through changes so slight that only instruments and careful geological reconstruction can reveal them. A fault may go years without obvious movement while its surrounding rock continues to store elastic strain. Then a short interval of slip releases part of that stored energy. Afterward, the process begins again, though not always from the same starting point. The fault and its surrounding crust carry a memory of past events. They do not return to a perfectly neutral state. Importantly, scientists do not speak of stress buildup as though it were a simple countdown. A highly stressed fault is not guaranteed to fail immediately, and a segment that has slipped recently is not guaranteed to remain quiet. The crust is too complex for such direct certainty. What can be said with confidence is that tectonic loading continues, that locked regions accumulate strain. and that the release of that strain through earthquakes or other slip changes the conditions for what follows. Where observations are strong, this build-up can be mapped in a relative sense. Where data are sparse, uncertainty remains. At this inward level, the fault system is understood not as scenery, not as fractured ground, and not only as a rough sliding surface, but as a loaded mechanical system storing energy in rock. The recent shifts on the two monster fault lines draw attention because they indicate a change in that stored state. Stress has been redistributed. Strain has been released in some places and remains in others. The crust around the fault has bent, held, and carried force through time. The motion has not yet been described as rupture. It is still the condition that precedes and surrounds rupture, the build-up of stress and the storage of elastic strain in rock under steady tectonic loading. Here, deep within the logic of the fault zone, the ground is waiting under pressure, held between resistance and release. When the stored strain in rock exceeds the strength and frictional resistance holding a fault in place, rupture begins. This beginning is not usually visible from the surface at first. It starts at depth, or within the fault zone as a small area where the boundary can no longer sustain the imposed stress. A patch fails, the opposing sides slip, and the sudden change in force alters the conditions around it. If the surrounding part of the fault is also near failure, the rupture expands. If not, it may remain limited. In either case, the essential process is the same. Rock that has been holding elastic strain releases part of that stored energy through rapid movement and through waves that travel outward across the crust. The point where rupture starts is often called the hypercenter. This is the place within Earth where the earthquake begins. Directly above it, at the surface, lies the epicenter. The epicenter is useful for mapping and communication, but the physical process originates below, along the fault surface or within the fault zone. From that starting place, rupture may travel along the fault in one direction or in both directions, depending on the structure and stress conditions. It does not leap across the whole fault at once. It propagates, meaning the zone of active breaking and slipping moves through the crust as neighbouring patches fail in sequence. This propagation can be very fast, often moving at a large fraction of the speed at which shear waves travel through the surrounding rock. A shear wave is a type of seismic wave in which particles move side to side relative to the direction the wave travels. The exact rupture speed varies from one event to another and from one segment of a fault to the next. Some ruptures remain moderate and limited. Others continue across long stretches of a major fault. The length of rupture. The amount of slip and the area of the fault that fails together help determine the size of the earthquake. As rupture advances, the two sides of the fault do not slide smoothly in a simple continuous way. Slip is often uneven. Some patches move more than others. Some areas may stop briefly while nearby parts continue. Stronger zones may resist until rising stress from surrounding slip overcomes them. Weaker zones may fail readily. The fault surface, with its asperities, roughness, and variable material, controls this pattern. The earthquake therefore becomes a dynamic process, a moving front of failure and release shaped by the details of the boundary through which it passes. The sudden movement generates seismic waves. These waves carry energy away from the rupture zone and through the surrounding Earth. One major type is the primary wave, often called the P wave. In a P wave, particles move back and forth in the same general direction that the wave travels. This makes it a compressional wave. It alternately squeezes and expands the material it passes through. P waves usually travel faster than other seismic waves and therefore arrive first at distant instruments. A second major type is the secondary wave, or S wave. In an S wave, particles move sideways relative to the direction of travel. S waves generally arrive after P waves and often produce stronger shaking because of the way they move the ground. At greater distances near the surface, additional wave types become important. Surface waves travel along Earth's outer layer rather than through its deeper interior. They often move more slowly than P and S waves, but they can produce prolonged and sometimes strong ground motion, especially in sediment-filled basins and near the surface where structures and loose ground are most affected. For scientists focused on the rupture process itself, these waves are valuable because their arrival times, amplitudes, and frequencies reveal details about where the earthquake started, how the fault slipped, and how energy was distributed through the event. Frequency refers to how rapidly a wave oscillates. Some seismic waves are high frequency, meaning they fluctuate rapidly. Others are low frequency, meaning their oscillation is slower. Different frequencies interact differently with rocks, sediments, and human structures. High-frequency energy may attenuate, which means weaken, more quickly with distance in some materials. Lower-frequency waves may travel farther and strongly affect large basins or tall buildings. The earthquake source influences this distribution, but so do the path through the crust and the properties of the ground near the surface. Scientists reconstruct rupture by combining many kinds of evidence. Seismometers record the sequence of arriving waves at different locations. GPS stations may detect permanent offsets caused by the slip. Radar interferometry may show the pattern of ground displacement after the event. Field observations may reveal fresh surface rupture if the fault breaks through to the surface. By integrating these data, researchers estimate how the rupture initiated, how fast it propagated, how much the fault slipped in different places, and how the energy release varied across the fault plane. This reconstruction is not a direct view of the moving rupture itself. It is an inference built from the signals the rupture leaves behind. Not every rupture reaches the surface. Some earthquakes occur entirely within the subsurface, releasing energy and generating waves without producing a clear visible break above. In those cases, the crust may still deform at the surface through warping or subtle displacement, but the main rupture remains buried. Other earthquakes do cut all the way upward, leaving fault scarps, offset roads, broken pipelines, or shifted stream channels. Whether rupture reaches the surface depends on the depth of initiation, the amount of slip, the strength of shallow materials, and the geometry of the fault zone. The release of elastic strain during rupture changes the surrounding stress field almost immediately. Areas near the slipped patch may be unloaded in one sense and newly loaded in another. This is why aftershocks often follow a main rupture. The crust is adjusting to the new pattern of force. Small remaining barriers fail, damaged zones settle into altered stress conditions, and neighbouring structures respond. Even so, the principal rupture remains the central event, the moment when stored energy is converted into motion, and waves on a larger scale than the preceding slow build-up. For the two monster fault lines being watched closely, the possibility of rupture matters because recent movement may represent either a limited adjustment or part of a broader process of stress release. If a notable rupture has already occurred, scientists study its geometry and wave field to understand what changed. If only smaller shifts have been detected so far, the mechanics of rupture remain central because they define what a larger failure would involve. The physics does not change with public attention. Rock still holds strain, friction still resists motion, and when failure begins, rupture and seismic waves remain the means by which the crust releases stored energy. At this inward level, The fault zone becomes a source of motion that radiates through Earth. The broad landscape has receded. The broken rock, sediment cover, instruments, shallow blocks, frictional contact, and stored stress have all narrowed toward this process. Rupture is the moment of failure. Seismic waves are the moving record of that failure traveling outward through the crust. Together they mark the conversion of long-accumulated strain into sudden mechanical release. Below the shallow, brittle crust, fault behavior begins to change. The same major structure that breaks rock offsets channels and produces ordinary earthquakes near the surface does not continue downward in exactly the same way at every depth. Temperature rises, pressure increases, minerals respond differently. The rocks remain under tectonic force, yet their manner of deformation becomes less uniform. Along this transition, some parts of a fault may remain locked and capable of sudden failure, while others begin to slip more gradually or deform without producing the same kind of sharp, brittle rupture. This is the region where the behavior of the two monster fault lines grows more complex because depth does not simply continue the shallow pattern, it transforms it. The upper seismogenic crust, where most ordinary tectonic earthquakes occur, depends on rock remaining brittle enough to fracture suddenly. As depth increases, however, the combined effects of heat and confining pressure alter how minerals carry stress. Confining pressure is the pressure applied from all directions by the surrounding rock. It tends to suppress the opening of cracks, while increasing temperature weakens many minerals and encourages more distributed deformation. The result is that faults may still localize strain at depth, but the style of motion changes. Instead of repeated brittle failure on all segments, some deeper parts begin to creep, glide slowly, or deform in a more ductile manner. Ductile means the material changes shape permanently by flowing or bending rather than by breaking abruptly. This transition does not occur at one single universal depth. It depends on rock type, geothermal gradient, fluid conditions, strain rate, and tectonic setting. In some continental regions, brittle faulting dominates through much of the upper crust before gradually giving way below. In other settings, the transition may be shallower or deeper. Scientists therefore do not assign one fixed number for where locked behavior ends and deeper creeping begins. Observations indicate that the transition zone is often broad and uneven, not a neat boundary. One segment of a fault may continue to host earthquakes deeper than another nearby segment, simply because local conditions differ. Along a major fault, a locked patch at intermediate depth can be especially important. If it resists slip while surrounding shallower or deeper parts deform more gradually, stress may become concentrated there. Such a patch can act as a bridge between surface faulting and deeper flow, holding strain within a portion of the fault system that remains capable of brittle or frictional failure. In this way, the distribution of locked and creeping zones with depth strongly affects where earthquakes nucleate and how ruptures propagate. A rupture that begins in one depth range may or may not continue into another, depending on how the fault strength changes downward. Deeper creeping zones do not imply the absence of tectonic motion. In many cases, they indicate that tectonic motion is being accommodated steadily rather than stored in the same elastic way as in locked brittle patches. This steady slip can load the locked region above. The deeper part continues to move under plate-driven forces, but the shallower locked fault cannot keep pace. The mismatch causes strain to accumulate in the upper crust. Thus, the deeper creeping section may help explain why stress continues to build in the shallower earthquake-producing part of the system. The deeper and shallower portions are mechanically connected, even though they behave differently. Scientists sometimes detect this contrast through geodetic data, and earthquake distributions. If surface measurements suggest ongoing tectonic loading, but small earthquakes cluster only within a certain depth band, that pattern may indicate a locked shallower section above a deeper creeping or transitional zone. Repeating earthquake signals on some patches may also point to stable slip occurring nearby. In other cases, slow slip events may be inferred, episodes of deeper or intermediate movement that release strain over days to months without producing a typical damaging earthquake. These events are not always easy to observe in continental fault systems, but where detected they reveal fault behavior that lies between clear locking and sudden rupture. The deeper transition zone may also host tremor in some settings. Tremor is a weak, prolonged seismic signal distinct from ordinary short, sharp earthquake waves. It is often associated with slow slip or distributed deformation near the brittle ductile transition in certain tectonic environments. Tremor is not observed equally on all faults, and its meaning depends strongly on context. But its existence shows that the fault zone can produce motion-related signals even when classic brittle rupture is absent. The mechanical state of the fault at these depths is therefore varied. It may include creeping slip, transient slow movement, tremor, localized brittle failure, and distributed ductile shearing in close association. Another important feature of this depth range is segmentation. The same fault may not transition smoothly everywhere. One section may remain locked to greater depth because colder or stronger rocks persist there. Another may weaken earlier because of elevated heat flow, altered minerals, or higher fluid pressure. Bends and stepovers in the fault geometry may also affect how stress is concentrated downward. As a result, the deep behavior of a major fault can be patchy along its length as well as with depth. This matters greatly for scientists watching two major fault lines after recent movement. Surface observations alone cannot reveal whether the deeper parts of those faults are creeping steadily, remaining partly locked, or adjusting through slow transient events. Yet those deeper conditions influence what the shallower system is likely to do. In this deeper region, the meaning of locking also becomes more subtle. Near the surface, locked commonly suggests that two sides of a fault are stuck in a way that stores clear elastic strain around them. At greater depth, where temperature and pressure alter deformation mechanisms, a segment may resist rapid slip without being fully locked in the shallow brittle sense. It may deform slowly by crystal scale processes, by distributed shearing across a broader zone, or by intermittent slip too gradual to radiate strong seismic waves. The opposition between locked and creeping is therefore useful but incomplete. Real deeper fault zones often occupy a continuum between those states. The energy budget of the fault system is shaped by this continuum. Deeper creeping can relieve some strain locally, but it can also transfer stress upward and along strike into more brittle locked regions. A fault is not safer simply because part of it is creeping. In some cases, creeping sections may reduce the likelihood of a large stress accumulation on that exact patch. In others, they may increase loading on neighboring locked asperities. Observations indicate that both outcomes are possible depending on geometry and coupling. Coupling refers to how strongly different parts of the fault system are mechanically linked in their motion. At the scale of rocks themselves, this depth range is where frictional sliding, distributed cracking, and plastic deformation may all begin to overlap. Individual minerals may deform internally, while the fault zone as a whole continues to localize strain. Fine-grained shear zones may develop. Older brittle fractures may be overprinted by smoother foliated fabrics, meaning planar mineral alignments formed by sustained deformation. Yet the structure still belongs to the same fault system traced at the surface. The monster fault line visible in the landscape above remains connected to this subtler zone below, where motion continues under hotter and more confined conditions. For scientists, this region is difficult to observe directly. Boreholes rarely reach the full depth of the transition on major continental faults, and direct sampling is limited. Much of the understanding comes from indirect methods, experimental rock mechanics, geophysical imaging, exhumed ancient fault zones now exposed at the surface, and the patterns of modern earthquakes and deformation. Some uncertainty remains in exactly how each fault behaves with depth, especially during changing stress conditions, yet the general picture is clear. The deeper part of an active fault is not simply an extension of the shallow rupture plane. It is a changing mechanical environment where locking weakens, creep may increase, and the fault moves toward the hotter interior. At this inward stage, the two monster fault lines pass from brittle near-surface failure into a deeper transition of mixed behavior. Some zones still hold, some slip slowly, some deform in ways that produce little obvious seismic release. The fault remains active, but its language changes with depth, becoming less abrupt and more thermally shaped as the crust moves toward the hotter and more pressured interior below. Deeper within the fault zone, heat, pressurized fluids, and changing minerals begin to alter the strength of rock in ways that are hidden from the surface, but essential to the behavior of the whole system. The fault is no longer defined only by broken blocks, frictional contact, stored stress, or the mixed, locked and creeping zones above. At this depth, the materials themselves are changing. Minerals respond to temperature. Fluids move through fractures and pores under pressure. New fabrics form as older brittle structures are overprinted by deformation under hotter conditions. The two monster fault lines remain part of the same tectonic system, yet the forces governing their motion are now increasingly chemical and thermal, as well as mechanical. Temperature rises with depth through the crust, although not always at the same rate in every region. This rise is called the geothermal gradient, meaning the increase in temperature downward from the surface. The exact gradient depends on crustal thickness, heat flow from below, rock type, and tectonic setting. As temperature increases, many minerals become less strong in the brittle sense and more able to deform by internal crystal scale processes. These processes are far too small to see directly in a living fault at depth, yet they change how strain is accommodated. A rock that would fracture suddenly in cooler shallow crust may begin to bend, recrystallize, or flow more gradually when it is hotter. Heat alone does not determine the behavior of the fault zone. Fluids matter as well. These fluids are usually water-rich, though they may contain dissolved salts, gases, and chemical components released from minerals during metamorphic reactions. Metamorphism is the process by which rocks change mineral structure and texture in response to heat, pressure, and fluids without fully melting. As temperature and pressure increase, some minerals break down and release water into the surrounding rock. That fluid may enter fractures, pore spaces, and shear zones, changing both mechanical strength and chemical reactions along the fault. One of the most important effects of fluid is the reduction of effective normal stress. Effective normal stress is the part of the force pressing fault surfaces together that is truly carried by the solid grain framework rather than supported by fluid pressure. If fluid pressure rises, the grains push less directly against one another. The fault may then slide more easily because frictional resistance is reduced. This does not mean that any fluid-rich zone will immediately fail. The rock still has strength, and geometry still matters. Yet elevated fluid pressure can make a crucial difference in whether a patch remains resistant or begins to slip. Scientists consider this one of the major hidden controls on fault strength at depth. Fluids also change minerals. Along shear zones, circulating water can promote the growth of new mineral assemblages that are mechanically weaker than the original rock. Feldspar-rich rocks, for example, may alter toward clay-rich or mica-rich compositions under suitable conditions, and these altered materials may deform more readily. Serpentine minerals, in settings where ultramafic rocks are present, can produce particularly weak zones under certain pressure and temperature conditions. Not every major continental fault contains the same mineral systems, and the exact chemistry varies from place to place. Even so, the broader principle remains consistent. Chemical alteration can transform a strong fault wall into a weaker shear zone over long periods of tectonic activity. As minerals change, so does rock texture. Fine-grained foliated fabrics may develop where sustained deformation aligns mineral grains into planar structures. A foliation is a repeated planar arrangement of minerals or textures produced by deformation and recrystallization. These fabrics can allow rock to deform more easily in certain directions, localizing shear into narrow zones even when ordinary brittle fracture becomes less dominant. In this way, mineral change and deformation reinforce each other. Heat and fluids help create new weak fabrics, and those fabrics then guide further movement. Pressurized fluids do not always move freely. In some places, the fault zone acts as a conduit, allowing fluid to migrate upward or along, strike through fractured and permeable pathways. In other places, sealed or clay-rich zones trap fluid, allowing pressure to build. This uneven fluid distribution means that one segment at depth may be comparatively dry and strong, while another nearby is fluid-rich and weaker. Such heterogeneity can influence where slow slip occurs, where tremor may be generated, and where deeper sections of a fault transfer stress into locked shallower parts. The deeper fault is therefore not chemically uniform. It is a patchwork of evolving mineral and fluid conditions. Heat also affects the rate at which minerals deform internally. At higher temperatures, diffusion becomes more efficient. Dislocations within crystals move more readily, and grains may recrystallize under stress. These are microscopic processes, but at the scale of a fault they permit permanent deformation without the same abrupt fracture seen in the upper brittle crust. The fault zone may still be narrow, and shear may still be localized, yet the dominant mechanism gradually changes. Rock begins to yield not mainly by breaking, but by rearranging itself internally. This is one reason the deeper transition zone can accommodate motion without generating ordinary large brittle earthquakes on every patch. The presence of fluids and mineral change can also influence seismicity in complicated ways. In some cases, rising fluid pressure may trigger brittle failure in otherwise stable zones by weakening contacts or altering stress locally. In other cases, fluid-rich altered zones may promote stable sliding and reduce the tendency for abrupt rupture. The outcome depends on the balance among pressure, mineralogy, temperature, strain rate, and fault geometry. Scientists therefore describe fluid effect with caution. Observations indicate that fluids are central to many fault systems, but the exact consequence is not identical in every setting. Ancient exhumed fault zones provide some of the clearest evidence for these deep processes. In certain mountain belts, rocks that once lay many kilometers below the surface are later uplifted and exposed by erosion. These rocks preserve mylonites, foliated shear zones, mineral veins, and altered fault rocks that formed under elevated temperature and pressure. A mylonite is a fine-grained rock produced by intense ductile shearing. Such exposures allow geologists to examine structures that were once deep within active faults. Though these ancient examples are not exact copies of any present-day system, they reveal how mineral change, fluids, and heat can reorganize a fault zone from within. For scientists watching two major fault lines after recent motion, these hidden processes matter because they influence how the deeper system feeds the shallower one. A hot, fluid-assisted, mineral-weakened zone may allow steady deformation at depth and transfer loading upward into more brittle locked sections. Alternatively, fluid pressure fluctuations may change resistance on intermediate depth patches and contribute to slow slip or localized seismic activity. The surface movement that draws attention may therefore be connected to changes taking place much deeper, where no direct visual observation is possible. Uncertainty remains substantial in this region. Direct measurements of temperature, fluid pressure, and mineral reactions within active major faults are limited. Geophysical imaging can suggest fluid-rich zones or anomalous structures, but it does not reveal every detail. Laboratory experiments show how minerals behave under controlled conditions, yet natural faults are more complex. Even so, the general framework is firm. As depth increases, heat rises, fluids interact with rock, minerals change, and fault strength evolves. The behavior of the system cannot be understood fully from mechanics alone. It is also a problem of chemistry and thermal state. At this inward layer, the two monster fault lines enter a hidden environment where motion is shaped by warm rock, pressurized water, and altered minerals. The fault is still a boundary, but it is now also a chemical and thermal pathway. The deeper the system goes, the more its strength depends on transformation from within. Beneath the broken surface world, beneath the monitored crust and stored strain, the fault is being changed by heat and fluids into the kind of structure that can keep moving through deep time. At the deepest layer of this story, the two monster fault lines are no longer understood mainly as scars in the crust, or even as shifting boundaries within a deforming fault zone. They are expressions of plate motion, the slow and persistent movement of vast sections of Earth's outer shell, driven by processes operating on a planetary scale. The surface fault, the damaged rock, the sediment, the instruments, the locked patches, the creeping depths, the heated minerals, and the moving fluids all belong to this larger tectonic system. Here, in the deepest region of explanation, the fault lines are seen as parts of plate boundaries or plate boundary zones, places where the long motion of Earth's lithosphere is translated into local stress and, eventually, into movement along specific faults. The lithosphere is the rigid outer layer of Earth, made up of the crust and the uppermost mantle. It is broken into tectonic plates that move relative to one another over the weaker, hotter asthenosphere beneath. The asthenosphere is not a liquid ocean of rock, but a region of the upper mantle where heat and pressure allow solid material to deform slowly over long periods. Because of this slow deformation below, the stronger lithosphere above can move as large plates. These motions are extremely slow by human standards, often measured in millimeters or centimeters per year. Yet over millions of years they reorganize oceans, raise mountains, open rifts, and maintain the stress that powers active fault systems. Not all plate boundaries are simple lines. Some are broad zones in which motion is distributed across many faults, basins, uplifts, and rotating crustal blocks. The two monster fault lines belong to such a tectonic setting in spirit even when they are individually mapped as distinct structures. Their movement reflects the larger requirement that one part of the lithosphere move relative to another. The plate system does not pause because one fault is temporarily locked. Motion continues to be imposed across the region, and the crust must find ways to accommodate it. If one major fault resists slip for a time, deformation may spread into neighbouring structures or accumulate as elastic strain until release becomes possible. The driving forces of plate motion are still studied in detail, and some uncertainty remains about their relative importance in different settings. Observations indicate that slab pull, ridge push, gravitational potential differences, and mantle flow all contribute in various ways. Slab pull refers to the force exerted by a cold, dense oceanic plate sinking into the mantle at a subduction zone. Ridge push refers to the gravitational sliding force that acts as newly formed lithosphere moves away from elevated mid-ocean ridges. Mantle flow describes the slow circulation of solid but deformable mantle material that can interact with the base of the plates. In continental fault regions, the exact contribution of each force may be less directly visible than at oceanic spreading centers or major subduction zones, but the result remains the same. Plate-scale motion transmits stress into the crust, and faults become the structures through which that stress is accommodated. A major fault line does not need to lie exactly on a clean plate edge to be plate-driven. Many continental regions consist of deforming boundary zones where motion is partitioned among several faults. Partitioning means that the total relative plate motion is divided into different components taken up by different structures. One fault may accommodate more sideways slip, another may absorb shortening through uplift and thrusting, another may allow extension and basin formation. The two monster fault lines being watched closely can therefore be understood as parts of a deeper tectonic budget. Their motion is one share of the larger relative displacement required by the plate system. This perspective explains why the faults remain active over such long spans of time. A landslide may happen once on a slope and then rest. A river may change course and later stabilize. But a plate-driven fault persists because its source of loading continues. As long as the plates move, stress is renewed. The fault may branch, migrate slightly, or change segment behavior through time, but the regional need for accommodation remains. The crust may break along old weaknesses because reusing them is mechanically easier than creating entirely new ones. In this sense, a fault is both a consequence of present tectonic motion and an inheritance from the tectonic past. The deepest origin of the two fault lines also explains why complete stillness is not a realistic long-term state. A locked segment may remain quiet for years or centuries, yet the plate system continues to load it. A creeping segment may release motion steadily. Yet the same plate system may concentrate stress on an adjacent locked patch. A recent small shift may represent only a minor adjustment within a much larger pattern of accumulated deformation. Scientists watch closely not because every movement is extraordinary, but because every movement is part of a persistent planetary process that does not stop at the scale of one event. At this depth of understanding, the fault lines are connected to mantle-scale time and space. The rocks near the surface break because the lithosphere as a whole is in motion. The frictional resistance along the fault plane matters because plate motion continues to push the system against that resistance. The deeper creeping zones matter because they are ways in which the lithosphere transmits motion through varying thermal and chemical conditions. Even the surface record in sediment and scarps becomes legible as part of this planetary conveyor of stress and displacement. Scientists also recognize that plate motion sets long-term rates, but does not determine the exact timing of individual events. The plates supply the loading. They do not provide a precise clock for rupture. Local fault geometry, friction, fluids, rock strength, and the legacy of previous earthquakes all influence when and how slip occurs. This is why scientists can say with confidence that a region remains tectonically active while still remaining uncertain about the exact evolution of a particular segment after recent movement. The deepest engine is steady. The local response is variable. Over millions of years, plate motion can reorganize entire fault networks. A fault that is dominant during one interval may become less important as deformation shifts to a neighboring structure. New basins may open, uplifts may grow, and old shear zones may be abandoned or reactivated. Yet within the timescale of human observation, the major fault lines often appear enduring because the plate framework changes far more slowly than individual earthquake cycles. The two monster fault lines now being watched belong to this middle scale, long enough to shape regions and recur through many generations, yet short enough to be observed with instruments and mapped through recent deformation. This deepest view also places caution around dramatic language. A monster fault is still a structure within the natural tectonic architecture of the planet. Its power comes not from sudden mystery, but from the slow accumulation of motion imposed over immense spans of time. When the fault moves, it is expressing the continuing work of Earth's lithosphere. The recent shifts matter because they reveal that the larger system is active here and now, transferring part of its planetary motion into a particular pair of crustal boundaries. What changes at the surface begins in this deep and patient engine. At the innermost level, the two fault lines are therefore not isolated objects at all. They are local manifestations of a moving planet. The crust fractures because the lithosphere is divided. The lithosphere moves because it rides above a hotter, deforming mantle. Stress is renewed because plate motion persists. From this deepest engine, the entire outer sequence becomes clear in reverse. Plate motion loads the fault system. Heat, fluids, and minerals alter it at depth. Locked and creeping zones shape its behavior. Stress builds, rupture occurs, waves travel, blocks shift, rocks fracture, sediment records the change, instruments detect it, and the landscape carries the trace across the surface of Earth. The land grows quiet again in the scientific view, though not because motion has ended. Quiet here means only that the visible surface returns to its ordinary pace. Wind continues across ridges and valley floors. Water follows channels cut through older layers of gravel and stone. Dust settles. Plants root into soil that has been lifted, shifted, fractured, and buried many times before. The two great fault lines remain where they have long been, extending through the crust as boundaries shaped by repeated strain. Their recent movement does not separate them from the rest of Earth. It places them back into it as part of the same steady tectonic process that builds mountains, opens basins, and slowly rearranges the outer shell of the planet. Scientists keep watching because the ground keeps recording. Instruments remain fixed in place. Satellite paths continue overhead. Small earthquakes may come and go. Some segments may hold. Some may slip by amounts too small for ordinary notice. The exact path ahead remains uncertain, as it must remain in a fault system governed by uneven rock strength, changing stress, friction, fluids, and the deep persistence of plate motion. Observations indicate what has changed. It remains uncertain how strain will next be partitioned across every segment and neighbouring structure. Even so, the deeper pattern is clear. Earth is not a still sphere covered by accidental cracks. It is an active world whose rigid outer shell is always under slow adjustment. Fault lines are among the clearest places where that adjustment becomes visible. They turn deep planetary motion into surface form, into measured displacement, into shaking, into scarps and shifted channels and broken rock. When two major fault lines move, the event feels immediate in human time. yet it belongs to a process far older and slower than any single life. The ground settles back into apparent calm, carrying within it the same quiet pressure that shaped it before and will continue shaping it long after the moment has passed.